From the very earliest moments of human consciousness, we have gazed up at the night sky with a sense of profound wonder and awe. That dark, star-dusted tapestry has always been a source of our greatest questions and our most enduring myths. Welcome, dear listeners, to the Restful Stories. We are so glad you have joined us for this journey into the cosmos. If you enjoy these explorations of the known and the unknown, please do take a moment to subscribe, ensuring you never miss our future stories. For millennia, our understanding of the heavens was woven from stories of gods and monsters, of celestial heroes and cosmic patterns that guided our seasons and our fates. But over time, a new kind of story began to be told, one of observation, mathematics, and a relentless desire to understand the fundamental rules that govern the universe. We learned to trace the paths of planets, to measure the distance to the stars, and to comprehend the immense gravitational dance that holds galaxies together. We built upon the shoulders of giants, from the patient astronomers of antiquity to the revolutionary minds of Copernicus, Kepler, and Newton, who together revealed a universe of elegant, clockwork precision. Yet, even Newton's profound insights into the nature of gravity, which reigned supreme for centuries, could not capture the universe's most bizarre and extreme possibilities. It was not until the early 20th century, with the arrival of Albert Einstein, that our story of the cosmos was torn apart and rewritten. Einstein gave us a new language to describe reality, a language of curved space-time, of gravity, not as a force, but as the very shape of the universe. Within his elegant equations of general relativity lay a prediction so strange, so unsettling, that even Einstein himself initially refused to believe it could be real. The theory described an object so massive and so dense that it would collapse under its own weight without limit, punching a hole in the fabric of space-time itself. It would create a gravitational field so powerful that at a certain point, a point of no return, the universe would be warped into a one-way street. It would be an object from which nothing, not even the fastest thing in existence, light itself, could ever escape. Tonight, we journey into the heart of this darkness to explore the nature, the history, and the profound mysteries of the objects we call black holes. In the vast, silent theater of the cosmos, there exist regions where the fundamental laws of physics are pushed to their absolute limits, where the familiar interplay of matter and energy gives way to an ultimate and inescapable conclusion. Here, gravity, the weakest of nature's fundamental forces, becomes an indomitable tyrant. We speak of a region in space where the pull of gravity is so profound, so overwhelmingly powerful, that its grip is absolute. Nothing that enters can ever leave. This is not a barrier that can be overcome with greater speed or more advanced technology. It is a fundamental feature of the universe's fabric. Even light, the fastest thing in existence, traveling at nearly 300,000 kilometers per second, or about 186,000 miles per second, is captured without hope of escape. The very concept of a place is redefined, becoming less a location and more a destination, a one-way journey into oblivion. This cosmic abyss is defined by a threshold of no return, a conceptual boundary that is as real as it is invisible. This demarcation is known as the event horizon. It is not a physical surface you could touch or see, but rather a mathematically defined sphere in space surrounding the central mass. Crossing the event horizon is an irreversible act. Once an object, a particle, or a beam of light passes this invisible precipice, its future contains only one possibility: a continued fall toward the center. The event horizon marks the point where the gravitational pull becomes so immense that the escape velocity required exceeds the speed of light, an impossible feat. The universe inside this boundary is causally disconnected from the universe outside. Events that occur within can never influence events in the wider cosmos. It is a silent, perfect prison, holding its secrets for eternity. The origins of these extraordinary objects are as dramatic as their nature. One of the established pathways to their creation involves the cataclysmic collision of incredibly dense celestial bodies. In the universe, there exist the collapsed cores of massive stars, known as neutron stars, objects so dense that a mere teaspoon of their substance would weigh billions of tons on Earth. When two such stellar remnants, locked in a decaying orbital dance, finally spiral into each other, the resulting merger is one of the most violent events imaginable. The collision unleashes a torrent of energy and gravitational waves, and in the aftermath, if the combined mass is sufficient, the fabric of space-time itself collapses, giving birth to a brand new stellar mass black hole. This process of creation through merger is not limited to neutron stars. In a universe populated by millions of these dark objects, it is inevitable that sometimes two black holes themselves will find each other. Drawn together by their mutual gravitational attraction over millions or even billions of years, they engage in a final, spectacular dance. As they spiral closer, they churn space-time with increasing ferocity, sending out powerful gravitational waves that ripple across the cosmos. The final moments are a crescendo of violence as their event horizons touch and merge, coalescing into a single, larger black hole. The new entity is more massive than the sum of its parts, with the difference in mass having been radiated away as pure energy in the form of those tremendous gravitational waves. While the formation of these stellar mass objects is understood, the genesis of their colossal cousins remains one of the great unsolved mysteries of modern astrophysics. Throughout the universe, particularly at the heart of most large galaxies, including our own Milky Way, lurk supermassive black holes, behemoths with masses ranging from hundreds of thousands to billions of times that of our Sun. How such giants formed in the early universe is a subject of intense debate among scientists. Perhaps they began as smaller black holes that grew voraciously over eons, consuming vast quantities of gas, dust, and stars. Or maybe they were born from the direct collapse of immense primordial clouds of gas, bypassing the typical star formation process entirely. The puzzle of their origin is a crucial piece in understanding the evolution of galaxies themselves. The prediction of these cosmic enigmas emerged not from the eyepiece of a telescope, but from the elegant equations of Albert Einstein's theory of general relativity, unveiled in the early 20th century. In 1915, Einstein proposed a new vision of gravity, describing it not as a force, but as the curvature of space-time caused by mass and energy. Yet, he was profoundly skeptical that the most extreme predictions of his own theory could manifest in reality. The mathematics pointed to the possibility of a singularity, a point of infinite density, which Einstein found philosophically unsettling, believing that nature would surely intervene to prevent such an absurdity. It was a classic case of a creator being unnerved by the full and bizarre implications of his creation. But the theoretical framework was sound, and the path it laid out was clear. Even as our understanding of these objects grew, they remained purely theoretical constructs for decades. It is one thing to predict an object's existence on paper, and quite another to find it in the sky. For a long time, the nearest black hole was a matter of speculation, but the precision of modern astronomical surveys has brought this distant concept much closer to home. The current title for the closest known black hole to Earth is held by an object named Gaia BH1, discovered by the European Space Agency's Gaia spacecraft, which is meticulously mapping the positions and motions of over 1 billion stars. This black hole is located approximately 1,560 light-years from our solar system. That distance, while vast on a human scale, is a mere stone's throw in cosmic terms. It translates to a staggering journey of nearly 15 quadrillion kilometers, or about 9.3 quadrillion miles. Gaia BH1 is part of a binary system, silently orbiting a star very similar to our own Sun, a quiet, cosmic neighbor whose presence was revealed only by its subtle gravitational influence on its luminous companion. For generations, the idea of actually seeing a black hole was considered impossible. By its very definition, it emits no light of its own. The breakthrough came not from a single instrument, but from a global collaboration that transformed our entire planet into a virtual observatory. In the year 2019, the Event Horizon Telescope project, a network of synchronized radio telescopes scattered across the globe, achieved what was once thought to be science fiction. They captured the first ever direct visual evidence of a black hole and its event horizon. This monumental achievement was the result of years of work, combining vast amounts of data to create an image of an object whose apparent size in the sky is comparable to a donut on the surface of the moon. The target of this ambitious observation was the supermassive black hole residing at the core of a distant galaxy known as Messier 87, or M87. This behemoth is located about 55 million light-years away from Earth. The image revealed a dark central region, the black hole's shadow, silhouetted against a blazing, asymmetrical ring of superheated gas and plasma swirling into the abyss. The scale of this object is almost beyond comprehension. Analysis of the image and subsequent data confirmed that the black hole at the heart of M87 possesses a mass equivalent to 6.5 billion times the mass of our own sun. All of that material is concentrated within a region of space not much larger than our solar system. This immense gravity is the engine that powers stupendous jets of energy that erupt from the galaxy's core, stretching for thousands of light years into intergalactic space. The image was a profound confirmation of Einstein's theories, showing that even at the most extreme edges of the universe, his equations held true. Despite their reputation as cosmic monsters, the gravitational influence of a black hole is often misunderstood. If our sun were to be instantaneously replaced by a black hole of the exact same mass, the effect on Earth and the other planets would be surprisingly anticlimactic. Our planet, along with Mars, Jupiter, and all the other bodies in our solar system, would continue to orbit this new, dark center just as they do now. The orbits would remain stable and unchanged because the gravitational field at our distance from the sun's center would be identical. We would be plunged into darkness and freeze, of course, but we would not be sucked in. A black hole's gravity is only inescapable when you get very close, once you cross the event horizon. From a safe distance, it behaves gravitationally, just like any other object of the same mass. This simple gravitational reality dismantles one of the most persistent myths found in popular culture: the image of black holes as cosmic vacuum cleaners, aggressively roaming the void and sucking in everything in their path. The truth is far more passive. A black hole is governed by the same laws of gravity as any other massive object. Its influence follows the predictable inverse square law, meaning its pull weakens dramatically with distance. It is only when an object's trajectory brings it perilously close, into the zone where tidal forces become extreme, and the gravitational well deepens precipitously, that its fate is sealed. A black hole simply waits, a silent trap in the fabric of space-time, for matter to wander too close. In a similar vein, the speculative fiction that portrays black holes as gateways to other dimensions or universes, while captivating, finds no support in our current understanding of physics. General relativity The very theory that predicts their existence describes a final destination within a black hole, not a cosmic shortcut. At the heart of a simple, non-rotating black hole lies a singularity, a point where the curvature of spacetime is predicted to become infinite, and all the mass is crushed into a region of zero volume and infinite density. Our current laws of physics, including general relativity itself, break down at this point, so we cannot definitively say what happens there. However, the established framework suggests it is an endpoint of spacetime, a place where time itself ceases, rather than a bridge to a different reality. These are features of our universe, not exits from it. Given that these objects are fundamentally invisible and are not cosmic portals, the question of their detection becomes a fascinating challenge. If a black hole emits no light, how can we possibly find it? The answer lies in observing its profound and violent effects on its immediate surroundings. When interstellar gas, dust, or even a wandering star ventures too close, it gets caught in the black hole's immense gravitational grip. This material does not fall straight in, but is instead pulled into a frantic, spiraling orbit. As more and more matter accumulates, it flattens into a vast, rotating structure known as an accretion disk. This disk is not a peaceful, swirling nebula. It is a place of unimaginable chaos and violence. The material within it, moving at speeds approaching that of light, experiences intense friction and compression. Gravitational energy is relentlessly converted into heat, raising the temperature of the disk to millions of degrees Celsius. A heat comparable to millions of degrees Fahrenheit. At these extreme temperatures, the matter glows with an incredible, searing brilliance. It unleashes a torrent of high-energy radiation, particularly in the form of X-rays and radio waves. This intensely bright accretion disk acts as a beacon, a cosmic lighthouse that signals the presence of the dark, unseen object at its center. Telescopes pointed at the sky, especially those sensitive to X-rays, can detect these telltale signatures, allowing astronomers to pinpoint the locations of black holes as they feast upon their surroundings. It is the final, desperate shriek of light from matter, just before it crosses the event horizon, that gives the game away. This is not the only way the unseen makes its presence known. The immense mass of a black hole provides another, more subtle clue. We can infer its existence by watching the graceful and sometimes frantic dance of the stars that orbit it. Just as we can deduce the mass of our sun by observing the orbits of its planets, astronomers can measure the mass of a dark, central object by tracking the paths of nearby stars. If they observe a star or a cluster of stars moving at incredibly high speeds in a tight orbit around a point in space that contains no visible object, the inescapable conclusion is that a massive, dark object must be lurking there. This very technique provided the irrefutable evidence for the supermassive black hole at the heart of our own galaxy, the Milky Way. For decades, astronomers at observatories like the European Southern Observatory in Chile and the Keck Observatory in Hawaii painstakingly tracked the movements of a small group of stars near the galactic center. They watched in awe as these stars, known as the S stars, executed impossibly fast and tight orbits around a single, invisible point. One star in particular, designated S2, completes an orbit in just under 16 years, reaching speeds of over 8,000 kilometers per second, which is about 5,000 miles per second, as it whips around its unseen partner. These observations, compiled over nearly 3 decades, allowed astronomers to calculate the mass of the central object with astonishing precision. It was determined to be approximately 4 million times the mass of our Sun, all confined within a region smaller than the orbit of Mercury. This monumental work, led by pioneers like Reinhard Genzel and Andrea Ghez, who were later awarded the Nobel Prize in Physics for their discovery, gave us our first definitive proof of the monster residing in our own galactic backyard, now known as Sagittarius A star. Sometimes the evidence is not a flash of light or a stellar dance, but a tremor in the very fabric of reality. When two black holes, locked in a cosmic embrace, finally spiral into each other and merge, the resulting cataclysm is so violent that it creates ripples in space-time itself. These disturbances, known as gravitational waves, propagate outward from the source at the speed of light, stretching and squeezing everything in their path. For a century, they were a purely theoretical prediction of Einstein's theory, thought to be too faint to ever be detected. But in 2015, that changed forever. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, a pair of exquisitely sensitive detectors in the United States, made the first direct detection of a gravitational wave. The signal was faint, a tiny chirp that lasted for a fraction of a second, but it was unambiguous. It was the echo of 2 stellar mass black holes, each about 30 times the mass of the Sun, merging into one in a distant galaxy over 1 billion years ago. This discovery opened an entirely new way of observing the universe, a form of astronomy without light, allowing us to listen to the silent, dark, cosmic events that were previously hidden from us. This new sense has allowed us to witness the universe's most extreme phenomena, providing a census of black hole mergers across cosmic history. The bizarre effects of a black hole's gravity extend beyond space-time ripples. As one approaches a region of such intense gravity, the flow of time itself is altered. According to general relativity, the stronger the gravitational field, the slower time passes. This phenomenon, known as gravitational time dilation, means that for an observer falling toward a black hole, their experience of time would be perfectly normal. However, to a distant observer watching their descent, their clock would appear to tick slower and slower as they neared the event horizon. Their movements would seem to decelerate, their final signals becoming stretched and redshifted until they appeared to freeze at the boundary, suspended for an eternity. They would never actually be seen to cross. This is not an illusion. It is a real difference in the experience of time. While this stretching of time occurs, the body of the unfortunate observer would be subjected to another, more gruesome effect. The gravitational pull of a black hole is not uniform. The part of an object closer to the black hole is pulled significantly more strongly than the part that is farther away. For an object falling in feet first, the gravitational pull on the feet would be immensely greater than the pull on the head. This vast difference in force, a super extreme tidal force, would stretch the object vertically. Simultaneously, the forces around the object would compress it horizontally. This process of being stretched into a long, thin strand of constituent atoms, like a piece of spaghetti, has been aptly and vividly named spaghettification. These phenomena, from gravitational waves to spaghettification, are common to all black holes, but the specifics can vary depending on the type of object. Astronomers now classify black holes into 4 main classes based on their mass. The smallest are the primordial black holes, a hypothetical type thought to have formed not from stars, but from the extreme density of the universe moments after the Big Bang. Next are the stellar mass black holes, the most common type, with masses ranging from a few to a few dozen times that of our Sun, born from the collapse of massive stars. Then there is the elusive and mysterious category of intermediate mass black holes, the cosmic middleweights ranging from hundreds to hundreds of thousands of solar masses, whose existence has only recently been confirmed. Finally, there are the giants, the supermassive black holes, the galactic anchors weighing millions to billions of solar masses that reside at the centers of most large galaxies. Each class represents a different scale of cosmic terror and a different piece of the universal puzzle. The most familiar of these cosmic behemoths are the stellar mass black holes. They are the direct descendants of the giants of the stellar world. A star many times more massive than our Sun leads a short and brilliant life, burning through its nuclear fuel at a ferocious rate. When the fuel in its core is exhausted, the outward pressure from nuclear fusion that had supported the star against its own immense gravity for millions of years suddenly ceases. In an instant, the star's core collapses catastrophically under its own weight. This implosion triggers a spectacular explosion in the star's outer layers, an event known as a supernova, which can briefly outshine an entire galaxy. What remains of the core, if it is massive enough, continues to collapse inward, crushing itself beyond the density of an atomic nucleus, beyond the state of a neutron star, until it forms a singularity. This process typically creates black holes with masses in the range of 5 to tens of times the mass of our Sun. Their size, defined by the diameter of their event horizon, is surprisingly small. A black hole of 10 solar masses would have an event horizon only about 60 kilometers, or roughly 37 miles across. These are the workaday black holes of the universe, scattered throughout galaxies like dark seeds from which more massive structures might eventually grow. They are the silent, invisible tombstones of once mighty stars. At the other end of the spectrum reside the true titans of the cosmos, the supermassive black holes. These are objects of almost unimaginable scale, true galactic royalty. Their masses are not measured in tens, but in hundreds of thousands, millions, or even billions of times the mass of our Sun. The very existence of such monsters poses a significant cosmological puzzle, as their formation mechanism is not as clearly understood as that of their stellar mass counterparts. Yet, their presence is undeniable. Nearly every large galaxy that we have observed, including our own Andromeda and Milky Way, appears to harbor one of these giants at its gravitational center, its downtown core. They act as cosmic anchors, with entire galaxies of hundreds of billions of stars orbiting them. The event horizon of a supermassive black hole is proportionally vast. For Sagittarius, a star with its mass of 4 million suns, the event horizon spans about 24 million kilometers, or 15 million miles, a distance that could comfortably contain the orbit of Mercury. For the M87 black hole at 6.5 billion solar masses, this boundary would extend far beyond the orbit of Pluto. These behemoths are not merely passive residents of their galaxies. They are active and influential agents, shaping the evolution of their galactic hosts through their powerful gravitational influence and the tremendous energy they release while feeding. Bridging the vast gap between these two well-established classes is a category that has long been a source of mystery and debate: the intermediate mass black holes. For many years, astronomers found plentiful evidence of small, stellar mass black holes and giant, supermassive ones, but nothing in between. It was as if the universe produced only bantams and heavyweights, with no middleweights in sight. This apparent absence was puzzling. As one might expect, a continuous spectrum of black hole masses. The existence of these intermediate objects, with masses ranging from 100 to hundreds of thousands of times that of the Sun, is still a frontier of active research. But tantalizing evidence has begun to emerge in recent years. Potential candidates have been identified near the centers of dense star clusters, known as globular clusters, and in the hearts of some smaller dwarf galaxies. Confirming their existence is crucial for our theories of cosmic evolution, as they may represent the seeds from which the supermassive black holes grew in the early universe, the missing link in the story of galactic formation. Their discovery has proven difficult precisely because they are not as disruptive as their larger cousins, and the environments where they are thought to reside are incredibly crowded and complex, making unambiguous detection a formidable challenge. The very nature of a black hole dictates that it cannot be seen directly. By definition, it is an object from which no light can escape, rendering it perfectly black against the black backdrop of space. It is a perfect absence of information. So how then can we speak with such confidence about their existence and properties? The answer is that we observe their presence not through light, but through shadow. We look for the undeniable mark they leave on their environment. One of the most dramatic forms of this indirect observation occurs when a black hole is not alone, but is part of a binary system with a star. If the star passes too close, the black hole's gravity can begin to strip away its outer layers of gas. This stolen material is pulled into the swirling, superheated accretion disk we have discussed, becoming a source of brilliant X-rays before it vanishes forever. Another, more catastrophic interaction can happen when a star on a wayward trajectory passes too close to a supermassive black hole. The immense tidal forces can stretch and rip the entire star apart in an event known as a tidal disruption event. The stellar debris is pulled into a long, bright streamer of gas, some of which is flung back out into space, while the rest is accreted by the black hole, causing a brilliant flare of radiation that can be seen across the universe. It is through these violent, luminous death throes of nearby matter that the invisible predator reveals itself. We see the crime scene, not the culprit. Our own galactic home, the Milky Way, is a sprawling spiral of several 100 billion stars, a vast, rotating disk of gas, dust, and dark matter. And at its very heart, some 26,000 light-years from Earth, in the direction of the constellation Sagittarius, lies the gravitational anchor of our galaxy, the supermassive black hole known as Sagittarius A star. Its presence, long suspected, was definitively confirmed through the meticulous tracking of those S stars executing their rapid orbits around the galactic center. Though it is a supermassive black hole, it is relatively modest and quiescent compared to those found in more active galaxies. Its current rate of consumption is very low, making the center of our galaxy a relatively calm place. However, evidence suggests that it was not always so peaceful. Faint remnants of past energetic outbursts, like giant bubbles of hot gas extending above and below the galactic plane, hint at a more violent, active past when Sagittarius A star was feasting more voraciously. Understanding its history and its current state is crucial to understanding the past and future of our own Milky Way. The life cycle that leads to the most common type of black hole begins with the largest and most luminous stars. These stellar giants, with masses many times that of our Sun, are cosmic blast furnaces, fusing heavier, and heavier elements in their cores. This process generates tremendous energy, pushing outward and balancing the inward crush of gravity. But this is a precarious balance. When the star has fused elements all the way up to iron in its core, it reaches a dead end. The fusion of iron consumes energy rather than releasing it. With its energy source gone, the core collapses in less than a second. This implosion is incredibly rapid, crushing the core to unimaginable densities and triggering a shock wave that propagates outward. This shock wave blasts the star's outer layers into space in a supernova explosion, one of the most brilliant events in the cosmos. The fate of the collapsed core depends on its mass. If it is below a certain threshold, it will stabilize as a dense neutron star. But if the core's mass is greater than about 2 to 3 times that of our Sun, no known force in the universe can halt the collapse. It will continue to shrink to a point of zero volume and infinite density, a singularity, creating a stellar mass black hole and leaving behind a dark remnant where a bright star once shone. The supernova explosion not only signals the death of the star, but also enriches the surrounding interstellar medium with heavy elements, which will eventually be incorporated into new stars and planets. A cosmic cycle of death and rebirth. This cycle of stellar collapse and supernova explosions is fundamental to the story of the universe. The very elements that make up our planet and our bodies, such as carbon, oxygen, and iron, were forged in the hearts of massive stars and then distributed throughout the galaxy by these spectacular explosions. The supernova is the star's final, magnificent act of creation. It is a profound piece of cosmic poetry that the formation of black holes, objects synonymous with destruction and oblivion, is inextricably linked to this life-giving process of elemental creation. The death of one star provides the raw material for the birth of countless others, and potentially for life itself. The black hole is the silent monument to this grand, violent, and ultimately creative cosmic cycle. The classification of black holes into these different types is a crucial framework for understanding their role in the cosmos. In essence, these objects are categorized into 3 main types based on their mass and origin: story, primordial, stellar, and supermassive. The primordial black holes, if they exist, are the theoretical relics of the Big Bang, formed not from stellar collapse, but from the immense pressures and densities of the nascent universe. They could, in theory, have a very wide range of masses, from smaller than an atom to many thousands of times the mass of the Sun. The stellar black holes, as we have seen, are the common type, the ghosts of massive stars. And the supermassive black holes are the galactic leviathans whose origins are still shrouded in mystery. This simple categorization helps astronomers to study how these different populations of black holes interact with their environments and how they might be related to each other. Perhaps through a process of hierarchical merging, where smaller objects combine over cosmic time to form larger ones. Of all these types, the primordial black holes are by far the most speculative and the smallest. They are a theoretical consequence of some models of the early universe, which suggest that in the first chaotic moments after the Big Bang, the density of energy and matter was not perfectly uniform. In regions where the density was significantly higher than average, the local gravity could have been strong enough to cause a direct collapse into a black hole. This process would not have required a star and could have produced black holes with a vast range of sizes, potentially including some with masses much less than that of a star. These tiny, ancient black holes, if they exist, could be wandering through the cosmos right now. Their detection is a major goal of modern astrophysics, as finding them would provide an unprecedented window into the extreme conditions of the universe in its very first second of existence. They are also considered a potential candidate for the mysterious dark matter that constitutes the bulk of the universe's mass, but does not interact with light. They are the ghosts of creation itself, a hypothetical population of objects that would rewrite our understanding of the cosmos, while the primordial black holes remain a tantalizing but unproven hypothesis. The stellar mass black holes are an established and ubiquitous feature of the cosmos. They represent the most common endpoint for the evolution of very massive stars, making them a frequent occurrence in any large galaxy. The Milky Way alone is estimated to contain a vast population of these dark remnants, with theoretical models and observational surveys suggesting that there could be anywhere from 10 million to as many as 1 billion of them scattered throughout our galaxy. Most of these objects are completely isolated, wandering silently and invisibly through interstellar space, having been born from a single star that collapsed without a binary companion. Their presence can only be inferred statistically or through rare, fleeting gravitational lensing events, where their gravity momentarily bends and magnifies the light of a more distant star passing behind them. A smaller fraction are found in binary systems, locked in an orbital dance with a companion star. It is this population that is most readily detectable, as the black hole's gravity strips material from its companion, creating the telltale accretion disks that blaze with high-energy X-rays. These X-ray binary systems are the lighthouses that allow us to map the distribution of black holes in our galactic neighborhood. The first of these systems to be identified and widely accepted as containing a black hole was a source in the constellation Cygnus, known as Cygnus X1. Its discovery in the mid-1960s marked a pivotal moment in the history of astronomy, transforming black holes from a purely theoretical concept into a tangible, observable reality. Cygnus X-1 was initially detected as one of the brightest and most variable sources of X-rays in the sky by instruments carried aboard sounding rockets. Subsequent observations revealed that this X-ray source was located at the same position as a massive blue supergiant star, designated HDE 226868. Astronomers observed that this star was wobbling, its light showing a periodic Doppler shift, indicating it was orbiting an unseen and incredibly massive companion. The orbital period was a mere 5.6 days, and the calculated mass of the invisible partner was far too large for it to be a normal star or even a neutron star. The only object that could fit the observational data, a compact object with a mass many times that of the Sun, was a black hole. This discovery was the smoking gun, the first solid piece of evidence that these strange objects predicted by Einstein's theory truly existed in the universe. The system became a natural laboratory for studying the physics of accretion and the behavior of matter in the most extreme gravitational environments imaginable. The black hole in the Cygnus X-1 system is a formidable object in its own right. Detailed studies of the binary's orbit have allowed astronomers to refine their measurements of its mass over the years. The current estimate places the mass of the black hole at about 21 times the mass of our Sun, making it one of the more massive stellar mass black holes known. All this mass is contained within an event horizon with a diameter of only about 124 kilometers, or roughly 77 miles. It is locked in a tight embrace with its companion star, from which it continuously siphons a powerful stellar wind. This captured material forms the intensely hot accretion disk that is responsible for the system's brilliant X-ray emission. The discovery of Cygnus X-1 was not without controversy, famously leading to a scientific wager between two giants of physics, Stephen Hawking and Kip Thorne. In 1974, Hawking, who was skeptical about the interpretation of the data, bet Thorne, a firm believer, a one-year subscription to Penthouse magazine, that the object was not a black hole. By 1990, the accumulating evidence had become so overwhelming that Hawking gracefully conceded the bet, acknowledging that Cygnus X-1 was indeed a black hole. This friendly wager symbolized the scientific community's gradual but ultimate acceptance of these once fantastical objects. It is crucial to remember that despite their fearsome reputation, black holes are only dangerous if one strays into their immediate vicinity. The danger zone is relatively small, confined to the region close to the event horizon, where tidal forces become extreme. From a safe distance, their gravity is no different from that of any other object of the same mass. The Earth is in no danger of being devoured by a black hole, as the nearest one, Gaia BH1, is a vast 1,560 light-years away. Even the supermassive black hole at the center of our galaxy, Sagittarius A star, poses no threat to us, as it is safely ensconced 26,000 light-years from our solar system. The universe is a odd and mostly empty place, and the chances of a random, wandering black hole passing close enough to our solar system to cause any disruption are infinitesimally small. Our celestial neighborhood is, for all intents and purposes, a safe harbor from these cosmic leviathans. The iconic image of the black hole at the center of the M87 galaxy, captured by the Event Horizon Telescope, provided a stunning visual confirmation of our theoretical models. The image does not show the black hole itself, as that is impossible, but rather its shadow cast against the glowing backdrop of the accretion disk. This shadow is a region of darkness, about 2.5 times larger than the event horizon itself, caused by the extreme bending of light by the black hole's gravity. It represents the point of no return for photons, the boundary of the photon capture sphere. The bright ring of light surrounding it is formed by photons from the superheated gas that are bent around the black hole, with some orbiting it multiple times before heading toward our telescopes. The fact that the ring appears brighter on one side is also a direct prediction of relativity, caused by the Doppler beaming effect, where the material in the disk moving toward us appears brighter than the material moving away. The image was a triumph, a perfect marriage of observational ingenuity and theoretical prediction, allowing us to see the unseeable by capturing its silhouette. The slowing of time near a massive object, a phenomenon we have touched upon, is a cornerstone of Einstein's theory and is known by the scientific term gravitational time dilation. This is not a speculative or hypothetical effect. It is a real, measurable phenomenon that has been confirmed by numerous experiments, both on Earth and in space. For example, clocks on GPS satellites, which are in a weaker gravitational field than clocks on the Earth's surface, have to be constantly corrected to account for the fact that they run slightly faster. The effect is tiny in our everyday lives, but near a black hole, it becomes extreme. For an astronaut orbiting a black hole, time would pass more slowly than for their mission controllers back on Earth. Upon returning from such a mission, they would find that they had aged less than their counterparts who remained in a weaker gravitational field. This effect is a fundamental consequence of the curvature of space-time. Gravity warps not only the 3 dimensions of space, but also the 4th dimension, time. The deeper one goes into a gravitational well, the more pronounced this temporal distortion becomes, a concept that has fueled countless science fiction narratives, but is rooted in solid scientific principles. The supermassive black hole in our own galactic backyard, Sagittarius A star, provides a specific and well-studied example of one of these cosmic giants. While it may be quiescent now, its mass is still immense, weighing in at approximately 4 million times the mass of our Sun. This mass was determined with high precision by tracking the orbits of the S stars for decades, a feat of observational astronomy that required pushing telescope technology to its absolute limits. The data from these stellar orbits allowed astronomers to apply Kepler's laws of planetary motion, the same laws that describe the orbits of planets in our solar system, to calculate the mass of the central object that was corralling these stars. The result was unambiguous. A huge amount of mass was packed into an incredibly small volume, leaving no other plausible explanation than a supermassive black hole. It is a relatively calm giant for now, but its sheer mass continues to govern the dynamics of the stars in the central region of the Milky Way. A quiet king holding court over a brilliant stellar entourage. Black holes are not static objects. They can and do grow over cosmic time. Their primary method of growth is through the process of accretion, the gradual accumulation of matter from their surroundings. This can involve the slow siphoning of gas from the interstellar medium, the dramatic tidal disruption of a passing star, or even the direct consumption of entire stars and gas clouds that stray too close. A more dramatic growth phase occurs when two galaxies collide and merge. During this chaotic process, the supermassive black holes at the centers of the two galaxies will eventually sink toward the center of the newly formed galaxy, where they will orbit each other and eventually merge, forming an even larger supermassive black hole. This hierarchical process of mergers and accretion is thought to be one of the primary ways that supermassive black holes have grown to their enormous sizes over the 13.8 billion year history of the universe. They are not born at their full size, but evolve and grow along with their host galaxies in a complex, symbiotic dance of coevolution. When a supermassive black hole is in a particularly active feeding frenzy, with vast amounts of material spiraling into its accretion disk, the system can become one of the most luminous objects in the universe. This intensely bright and energetic phenomenon, powered by the gravitational energy of the black hole, is known as a quasar. The name is a contraction of quasi-stellar radio source, as they were initially mistaken for stars when first discovered in the 1950s and 1960s. Quasars are the brilliant beacons of the young universe, visible across billions of light years. They are so bright that they can outshine their entire host galaxy by a factor of hundreds or even thousands. The light we see from the most distant quasars began its journey when the universe was only a fraction of its current age, providing astronomers with a glimpse into the cosmic dawn. They represent a key phase in the life of a supermassive black hole and the evolution of a galaxy, a period of rapid growth and immense energy output that profoundly affects the surrounding galactic environment. The gruesome process of spaghettification, the vertical stretching and horizontal compression of an object falling into a black hole, is a universal feature of these objects, but its intensity and the location where it becomes lethal depend critically on the black hole's mass. Counterintuitively, the spaghettifying tidal forces are much stronger near a smaller, stellar mass black hole than they are near a supermassive one. This is because the tidal force depends on the gradient of the gravitational field, which is much steeper for a smaller, more compact object. An astronaut falling toward a 10 solar mass black hole would be torn apart by these tidal forces long before they ever reached the event horizon. For a supermassive black hole like Sagittarius, a star, however, the gravitational gradient at the event horizon is much gentler. An astronaut could cross the event horizon of a supermassive black hole without immediately feeling any discomfort from tidal forces. The spaghettification would still happen, but it would occur much later, closer to the central singularity. This means one could, in principle, cross the point of no return of a supermassive black hole intact, only to be inevitably stretched into a stream of atoms in the unseen and unknowable region within. While the inward pull of a black hole is its defining characteristic, these objects are also responsible for some of the most powerful outflows of energy observed in the universe. In a process that is still not fully understood, the chaotic, swirling accretion disk around a feeding supermassive black hole can act as a colossal cosmic engine, launching powerful, collimated streams of particles and radiation back out into space. These outflows, known as relativistic jets, are truly stupendous phenomena. They erupt from the poles of the black hole perpendicular to the plane of the accretion disk and travel outward at speeds approaching that of light. These jets can extend for hundreds of thousands or even millions of light years, far beyond the confines of their host galaxy. They plow through the intergalactic medium, heating gas, triggering shock waves, and carving out immense cavities. The energy carried by these jets is so enormous that it can have a profound impact on the evolution of the entire galaxy. This process, known as feedback, can regulate star formation by blowing away the cold gas that serves as stellar fuel, effectively quenching the birth of new stars. In this way, a supermassive black hole, while consuming matter at the galactic center, can also dictate the pace of life and death for stars throughout its galactic domain, acting as both a creator and a destroyer on a cosmic scale. The extreme warping of space-time around a black hole has also led to one of the most intriguing and speculative ideas in theoretical physics, the concept of a wormhole. First explored in the 1930s by Albert Einstein and his colleague Nathan Rosen, the mathematics of general relativity permit solutions that describe a bridge connecting two different points in space-time. This theoretical structure, initially called an Einstein-Rosen bridge, and now popularly known as a wormhole, could hypothetically connect two distant regions of our universe, or even link our universe to another one entirely. Some scientists have theorized that the singularity at the center of a rotating black hole might not be a point of infinite density, but could instead be a gateway to such a wormhole. However, this remains firmly in the realm of speculation. Even if such structures are mathematically possible, they are predicted to be incredibly unstable, collapsing in an instant if even a single photon tried to pass through. Furthermore, creating and sustaining a traversable wormhole would require the existence of exotic matter with negative energy density, a substance that has never been observed and whose existence is purely hypothetical. While the idea of using a black hole as a cosmic shortcut is a staple of science fiction, our current understanding suggests that it is, for now, an impossible dream. Our exploration of the cosmos has revealed that black holes are not rare, exotic curiosities, but a common and integral part of the galactic ecosystem. The Milky Way galaxy, our cosmic home, is believed to be teeming with them. While the exact number is difficult to determine, current estimates based on stellar evolution models and our understanding of star formation rates suggest that there are likely millions, and possibly up to 1 billion, stellar mass black holes scattered throughout our galaxy. The vast majority of these are isolated and invisible, the dark remnants of stars that have long since ended their lives. They drift silently through the interstellar void, their presence only occasionally betrayed by a chance gravitational encounter. This large population of unseen objects contributes to the overall mass of the galaxy, playing a subtle but important role in its gravitational dynamics. Finding and cataloging these dark residences is a major goal for future astronomical surveys, as it would provide a much more complete census of our galaxy's contents and a deeper understanding of its history of star formation and death. Given this large population, it is natural to wonder about the possibility, however remote, of a close encounter. What would happen if a rogue, wandering black hole were to pass through our solar system? The scenario is extremely unlikely, given the vast distances between stars, but it is a fascinating thought experiment. The effect of such a passage would depend critically on the black hole's mass and its trajectory. If a stellar mass black hole were to pass through the outer reaches of the solar system, beyond the orbit of Neptune, its gravitational influence would be minimal, perhaps subtly perturbing the orbits of comets in the Oort cloud, but leaving the inner planets largely unaffected. However, a closer pass would be catastrophic. A black hole traversing the inner solar system would wreak havoc on the finely tuned gravitational balance that keeps the planets in their stable orbits. Planets could be flung into new, eccentric orbits, ejected from the solar system entirely, or sent on a collision course with each other or with the Sun. The Earth itself could be thrown into a frozen exile in interstellar space, or sent spiraling into the Sun. It is important to reiterate that the probability of such an event is vanishingly small, a cosmic traffic accident of the highest and most improbable order. The gravitational field of any object becomes more intense as you get closer to it, but for a stellar mass black hole, This change is particularly dramatic because all of its mass is concentrated into an infinitesimally small point. The singularity, the gravitational gradient, or the rate at which the force of gravity changes with distance, is incredibly steep. This extreme gradient is the very reason for the powerful tidal forces that cause spaghettification. Over a very short distance, say from your head to your feet, the difference in the gravitational pull can be enormous. For larger, supermassive black holes, this gradient is much gentler at the event horizon, as their mass is distributed over a much larger volume of space, as defined by their Schwarzschild radius. This is why the spaghettification effect is so much more pronounced near smaller black holes. It is a world where the familiar laws of gravity are pushed to an almost absurd extreme, where the difference of a few feet in position can mean the difference between feeling a gentle pull and being torn apart by an irresistible cosmic force. The origin of the smallest and most hypothetical class of black holes, the primordial black holes, is thought to lie in the very first moments of the universe's existence. In the instant following the Big Bang, the universe was an incredibly hot, dense, and chaotic soup of fundamental particles and energy. The conditions were so extreme that the density of matter and energy fluctuated wildly from place to place. According to some cosmological models, it is possible that in regions where the density was exceptionally high, the local gravity could have been strong enough to overcome the immense outward pressure of the primordial soup and trigger a direct collapse, forming a black hole. This process, occurring before the first stars had even formed, could have created black holes with a very wide range of masses, from microscopic objects with the mass of an asteroid to much larger ones weighing thousands of solar masses. The search for these ancient relics is one of the most exciting frontiers in cosmology, as their discovery would not only confirm these models of the early universe, but could also solve the long-standing puzzle of dark matter. The story of these smallest primordial black holes may have a unique and explosive ending. In 1974, the physicist Stephen Hawking made a groundbreaking theoretical discovery that combined the laws of general relativity with quantum mechanics. He predicted that black holes are not entirely black. Due to quantum effects near the event horizon, they should emit a faint glow of thermal radiation, a phenomenon now known as Hawking radiation. This process causes the black hole to lose mass and energy over time and to very slowly evaporate. The rate of this evaporation is inversely proportional to the black hole's mass, meaning that smaller black holes radiate away their mass much faster than larger ones. For a stellar mass or supermassive black hole, the process is incredibly slow, taking far longer than the current age of the universe. However, for a small primordial black hole, the process could be much faster. The very smallest of these objects, those with the mass of a mountain or less, would have had enough time to completely evaporate by now. Their final moments would be a brilliant flash of high-energy gamma rays, an explosive end to a life that began in the fire of the Big Bang. Searches for these distinctive gamma ray bursts have so far come up empty, placing limits on the number of small primordial black holes that could exist in our universe. Returning to the realm of the confirmed, the vast majority of stellar mass black holes that we have observed fall into a relatively narrow mass range. They are typically found to be between 5 and 15 times the mass of our Sun. This is a direct consequence of the physics of massive stars and supernova explosions. The mass of the final remnant is determined by the initial mass of the star and the complex details of how it sheds its outer layers during its life and in the final supernova. For a long time, there appeared to be a mass gap with very few black holes observed between about 2 and 5 solar masses, the region between the heaviest neutron stars and the lightest black holes. There was also a scarcity of observed black holes, with masses above about 20 solar masses. This suggested that our understanding of the final stages of stellar evolution was perhaps incomplete, or that there were observational biases that made it harder to find black holes in these mass ranges. This picture was dramatically changed by the dawn of gravitational wave astronomy. The Laser Interferometer. Gravitational Wave Observatory, LIGO, and its partner observatory Virgo have revolutionized our study of black holes. Since 2015, they have detected the ripples in space-time from dozens of binary black hole mergers. These detections have unveiled a population of black holes that were previously hidden from us. Many of the merging black holes detected by LIGO have masses that fall squarely in the upper mass gap, with some weighing in at 30, 40, or even more solar masses. In one extraordinary event, GW 190521, LIGO detected the merger of 2 black holes, weighing about 85 and 66 solar masses, which formed a new black hole of about 142 solar masses. This was the first definitive detection of an intermediate mass black hole. These gravitational wave observations have filled in the gaps in our black hole census, revealing that the universe is producing black holes with a much wider range of masses than we previously knew, and forcing astrophysicists to revise their models of stellar evolution and death. The detection of GW 190521 was a landmark event because it provided the first direct evidence for the existence of intermediate mass black holes. These objects, with masses ranging from 100 to hundreds of thousands of times that of the Sun, had long been the missing link in the family of black holes. Their formation mechanism is still debated. They might be formed through the runaway collision of massive stars in the dense cores of globular clusters, or they could be the remnants of the very first generation of stars, known as population 3 stars, which are thought to have been much more massive than the stars we see today. Another possibility is that they are primordial black holes formed in the early universe. The discovery of this new population of black holes by gravitational wave observatories has opened up a new field of study and provides a crucial piece of the puzzle of how the supermassive black holes at the centers of galaxies came to be. It is possible that these intermediate mass black holes are the seeds, the building blocks, that merged over cosmic time to form the galactic giants we see today. Following the monumental success of imaging the supermassive black hole in the galaxy M87, the Event Horizon Telescope collaboration turned its gaze inward, toward the heart of our own Milky Way. The target was Sagittarius A star, a far more challenging subject despite its relative proximity. It is 40 times less massive and nearly 2,000 times closer, which results in a shadow that appears roughly the same size in the sky as M87's. However, the gas swirling around Sagittarius A star orbits in a matter of minutes, not days, meaning its appearance changes rapidly. Imaging this flickering, dynamic target was like trying to take a clear picture of a spinning top. After years of painstaking work, combining data from a global network of radio telescopes and developing sophisticated new imaging algorithms to account for the rapid variability, the collaboration succeeded. In the year 2022, they released the second ever direct image of a black hole, that of Sagittarius A star. The image, remarkably similar to the first, showed a dark central shadow surrounded by a bright ring of glowing gas, confirming the presence of a black hole at our galaxy's center beyond any doubt. It was another stunning validation of Einstein's theory of general relativity, which once again predicted the size and shape of the shadow with uncanny accuracy. Seeing the dark heart of our own galaxy for the first time was a profound and deeply resonant moment for astronomy. A common misconception about black holes is that they are simply empty voids or holes in the fabric of space. This is a natural but inaccurate interpretation of their name. In reality, a black hole is the very opposite of empty space. It is a region containing an immense amount of matter that has been crushed into an incredibly small volume. All the mass of the original star or gas cloud that collapsed to form the black hole is still there, locked away behind the event horizon. The name black hole refers to its effect on its surroundings, its ability to trap light and create a region from which nothing can escape, making it appear as a black void. But the object itself is a concentration of matter and energy so extreme that it has fundamentally altered the geometry of space-time around it. It is not an absence, but a presence of the most profound and gravitationally dominant kind. The matter is there, but it is forever hidden from our view, its properties and state a mystery that lies on the other side of an impenetrable causal boundary. At the very center of this concentration of matter, according to the classical theory of general relativity, lies the ultimate cosmic mystery, the singularity. This is a point of theoretically zero volume and infinite density, where all the mass of the black hole is concentrated. It is a place where the curvature of space-time becomes infinite, and the laws of physics, as we currently understand them, including Einstein's own equations, break down completely. We cannot describe what happens at a singularity. It represents a boundary, not just in space, but a boundary of our knowledge. Most physicists believe that the concept of an infinitely dense point is a sign that general relativity is incomplete, and that a new, more fundamental theory is needed to describe such extreme conditions. This future theory, often referred to as quantum gravity, would merge the principles of general relativity with those of quantum mechanics, and would, it is hoped, resolve the paradox of the singularity, replacing it with a description of a finite, albeit incredibly dense, state of matter. Unlocking the secrets of the singularity is one of the holy grails of modern theoretical physics, a problem that could revolutionize our understanding of space, time, and matter. The sheer number of stars in our galaxy provides a powerful clue to the vast population of black holes it must contain. The Milky Way is estimated to be home to between 100 and 400 billion stars. A fraction of these are massive enough to end their lives as black holes. By combining our knowledge of star formation rates throughout the galaxy's history with our theories of stellar evolution, astronomers can create statistical models to estimate the number of stellar mass black holes that should exist today. These models consistently arrive at staggering numbers, suggesting that our galaxy is populated by a vast, unseen graveyard of between 10 million and 1 billion of these dark stellar remnants. This enormous population, mostly invisible and isolated, contributes significantly to the total mass of the galaxy and represents a fundamental component of its ecosystem. They are the silent majority, the dark legacy of billions of years of stellar birth and death, a hidden population that we are only just beginning to uncover through the subtle whispers of gravitational waves and the fleeting flickers of microlensing events. Extrapolating this to the grander cosmic scale paints an even more staggering picture. Our galaxy is just one among countless others in the observable universe. Current estimates, based on deep field observations from the Hubble Space Telescope and other powerful observatories, suggest that there are somewhere between 100 billion and 200 billion galaxies in the cosmos that we can see. If our Milky Way, a typical large, spiral galaxy, contains millions of stellar mass black holes and a supermassive one at its center, it is reasonable to assume that most of these other galaxies are similarly populated. Multiplying these numbers leads to an almost incomprehensibly large figure for the total number of black holes in the observable universe, a number that would be in the trillions or even quadrillions. This implies that black holes are not just a feature of galaxies, but a fundamental and ubiquitous component of the universe's structure and evolution. The cosmos is filled with these dark objects, from the stellar mass remnants that pepper galactic disks to the supermassive giants that anchor their very centers. They are an integral part of the cosmic tapestry, woven into the fabric of space-time on every scale. The anthropomorphic image of a black hole as a predator, actively hunting for matter to consume, is a compelling but misleading trope from science fiction. In reality, black holes are entirely passive objects, subject to the same laws of gravity and motion as any other celestial body. They do not have a will or an intent to suck things in. Matter falls into a black hole only if its orbit or trajectory brings it within the black hole's gravitational sphere of influence and ultimately across its event horizon. For an object on a stable orbit at a safe distance, a black hole is no more dangerous than a star of the same mass. It is a cosmic hazard that must be approached to be a threat, not a hunter that seeks out its prey. The dramatic accretion events we observe are the result of unfortunate stars and gas clouds that have wandered too close, their paths dictated by the complex gravitational dance of the galactic environment. The black hole is simply the passive beneficiary of these chance encounters, a silent, gravitational trap waiting for the cosmos to deliver its next meal. The process of accretion onto a supermassive black hole is not always a one-way street. While a great deal of material is consumed, the chaotic and energetic environment of the accretion disk can also lead to some spectacular ejections. Astronomers have observed supermassive black holes ejecting what can only be described as planet-sized spitballs of matter. These are dense clumps of gas with masses comparable to planets that are formed in the swirling accretion disk. Before they can be consumed by the black hole, complex magnetic fields and radiation pressure can accelerate these clumps and fling them out of the system at incredible speeds. These cosmic spitballs can travel at a significant fraction of the speed of light, launched on a journey that will take them far out into their host galaxy, or even into the desolate void of intergalactic space. This process demonstrates the incredible power and complexity of accretion disk physics, showing that the region around a black hole is not just a place of consumption, but also a powerful cosmic accelerator and ejector of matter. The formation of these extraordinary projectiles is a testament to the extreme conditions found in the immediate vicinity of a supermassive black hole. The accretion disk is not a smooth, uniform flow of gas. It is a turbulent, magnetized, and chaotic environment where matter is subjected to immense gravitational and magnetic forces. As gas swirls inward, it can fragment and form dense clumps. These clumps can then become entangled in the powerful magnetic field lines that are generated by the rotating disk and the black hole itself. Like a stone caught in a slingshot, these clumps of matter can be rapidly accelerated along the magnetic field lines and ejected away from the disk before they have a chance to cross the event horizon. This is a messy and inefficient form of eating, where a significant fraction of the incoming material is violently expelled before it can be consumed. These ejected spitballs are another piece of the complex feedback mechanism by which black holes interact with and influence their larger galactic environment. Intriguingly, the influence of a supermassive black hole can extend beyond simply consuming or ejecting matter. It can also play a direct role in the birth of new stars. The standard picture of star formation involves the slow gravitational collapse of large, cold clouds of molecular gas. It was once thought that the energetic environment around a supermassive black hole would be too violent and disruptive for this process to occur. However, observations have revealed the surprising presence of young, massive stars in very close orbits around Sagittarius A star, right at the heart of our galaxy. The existence of these stars in such a hostile environment was a major puzzle. It is now believed that the intense pressure and turbulence generated by the black hole's accretion disk and outflows can, under certain conditions, compress nearby gas clouds, triggering their collapse and initiating a burst of star formation. The black hole's influence is a double-edged sword. It can blow away the gas needed for star formation on a galactic scale, while simultaneously compressing gas in its immediate vicinity to create new stars. Some of the stars that are born in the chaotic environment near a supermassive black hole are destined for a lonely existence. The gravitational dynamics in the dense stellar cluster surrounding the black hole are incredibly complex. Close encounters between stars, or between a star and a binary system, can act as a powerful gravitational slingshot. Occasionally, these interactions can impart a tremendous amount of kinetic energy to a star, accelerating it to such a high speed that it is completely ejected from the galaxy. These hypervelocity stars are flung out into intergalactic space at speeds of millions of kilometers per hour, or millions of miles per hour, fast enough to escape the gravitational pull of the entire Milky Way. They are cosmic exiles, doomed to wander the vast, empty void between galaxies for the rest of their existence. The discovery of these stars provides dramatic evidence of the powerful gravitational interactions that take place in the extreme environment at the heart of our galaxy, a region where the supermassive black hole's influence can launch entire suns on a journey to nowhere. The influence of a supermassive black hole extends far beyond its immediate neighborhood, playing a crucial role in the large-scale evolution of its host galaxy. This intricate relationship is often described as a form of cosmic self-regulation. The supermassive black hole at the galactic center and the galaxy's stellar population appear to grow in a strangely synchronized manner, a phenomenon encapsulated in what is known as the M-sigma relation. This empirical correlation shows a tight relationship between the mass of the central black hole and the velocity dispersion of the stars in the galaxy's central bulge. In simple terms, bigger galaxies have bigger black holes. This suggests a deep, symbiotic connection governed by a feedback loop. When the black hole is actively feeding and growing, it unleashes tremendous energy in the form of radiation and powerful jets. This energy output heats up and blows away the cold gas in the galaxy, effectively shutting down star formation. As the gas supply is depleted, the black hole's own growth slows down. The galaxy then enters a quiescent phase, during which gas can cool and accumulate, eventually triggering a new burst of star formation. This, in turn, provides a new source of fuel for the black hole, and the cycle begins again. Through this process, the supermassive black hole acts as a galactic thermostat, regulating the rate of star formation and ensuring that the galaxy does not grow too quickly or burn through its fuel too rapidly. The groundbreaking images of black holes were made possible by a remarkable feat of global scientific collaboration and technological ingenuity known as the Event Horizon Telescope, or EHT. This is not a single, conventional telescope, but a virtual observatory created by linking together and synchronizing a network of existing radio telescopes located at high-altitude sites all around the world. From the Atacama Desert in Chile to the volcanic peaks of Hawaii, from the mountains of Arizona to the South Pole. This technique, called Very Long Baseline Interferometry, or VLBI, allows astronomers to achieve an angular resolution that is equivalent to that of a single telescope the size of the entire Earth. By combining the signals from these disparate locations, the EHT can resolve details so fine that it would be like seeing an orange on the surface of the moon. This incredible precision was absolutely necessary to capture the image of the black hole's shadow, an object whose apparent size in the sky is incredibly small. The EHT is a testament to the power of international cooperation, bringing together hundreds of scientists and engineers from around the globe to achieve a common goal that was once thought to be beyond the reach of science. In recognition of the profound cultural significance of the first black hole image, the team gave it a special name rooted in the heritage of the place where some of the most critical telescopes were located. The black hole at the heart of the galaxy M87 was given the Hawaiian name Pauehi. This evocative name is derived from the Kumulipo, a traditional Hawaiian creation chant, and can be translated as the embellished dark source of unending creation. The name beautifully captures the dual nature of a black hole. The Po, a deep, dark, and endless source, and the Wehi, an embellished, or honored form of darkness. It reflects the object's appearance, a dark shadow adorned with a brilliant ring of light, and its cosmic role as a powerful engine that shapes the evolution of its galaxy. The naming was a way of honoring the deep traditions of astronomical observation and a sense of place that have existed in Hawaii for centuries, connecting a cutting-edge scientific discovery to a rich and ancient cultural heritage. The universe's largest structures are not randomly distributed, but are organized into a vast filamentary network known as the cosmic web. Galaxies and galaxy clusters are found along the dense filaments of this web, separated by immense, nearly empty regions called voids. In a discovery that hints at the profound influence of these large-scale structures, astronomers have observed a startling alignment in a distant part of the universe. They found a group of supermassive black holes at the centers of quasars, all located billions of light-years away, whose relativistic jets are all pointing in roughly the same direction. This is a highly unusual and statistically significant alignment, as the orientation of a black hole's spin, and thus its jets, is typically thought to be random, determined by local accretion events. This large-scale coherence suggests that the black holes may have been influenced by a common environmental factor during their formation in the early universe. The most likely explanation for this remarkable alignment is that these black holes were formed within the same massive filament of the cosmic web. The primordial gas that flowed along these cosmic highways in the early universe may have had a coherent angular momentum, a large-scale spin that was imparted to the galaxies and the supermassive black holes that formed within it. This would mean that the alignment we see today is a fossil record, a preserved memory of the initial conditions in which these galaxies were born. It is a stunning piece of evidence that the largest structures in the universe can have a direct and measurable influence on the properties of individual objects like black holes, connecting the vast cosmological scale to the relatively small scale of galactic nuclei. This discovery provides a new window into the processes that governed the formation of galaxies and their central black holes in the infant cosmos. While many black holes announce their presence through the brilliant fireworks of their accretion disks, a new and more subtle class of these objects has recently come to light. Astronomers have found evidence for what they are calling stealth black holes, objects that are consuming matter at such a low rate that they are almost undetectable. Unlike the brilliant quasars or X-ray binaries, which are in a state of a feeding frenzy, these stealthy black holes are on a starvation diet, accreting matter so slowly and inefficiently that they produce very little radiation. Their accretion disks are faint, tenuous, and difficult to observe. These objects are found by detecting the gentle gravitational influence they exert on their surroundings, such as the subtle motions of companion stars or the slight warping of light from distant sources. The discovery of this quieter population suggests that our previous census of black holes, which relied heavily on detecting bright accretion phenomena, may have been incomplete. There could be a vast, hidden population of black holes lurking in the dark, quietly going about their business without drawing attention to themselves. A simple, non-rotating black hole, known as a Schwarzschild black hole, is a remarkably simple object, characterized by only a single property: its mass. The classical model of such a black hole, derived from Einstein's equations, can be broken down into three main components. The outermost boundary is the event horizon, the one-way membrane that separates the interior of the black hole from the rest of the universe. This is the point of no return. The second component, deep inside, is the singularity, the point of infinite density where all the mass is concentrated. A more complete model, which includes the effects of rotation, known as a Kerr black hole, introduces a third component, an inner event horizon. In this model, the singularity is not a point, but a ring. And the region between the two event horizons has bizarre properties where the roles of space and time are interchanged. The existence and properties of this inner structure are highly theoretical and may be altered by quantum effects, but it is a fascinating prediction of general relativity. One of the common misconceptions about the event horizon is that it is a place of immense and violent gravity. While the gravity there is certainly strong enough to trap light, the local gravitational force experienced by an object crossing the event horizon is not necessarily extreme. In fact, for a supermassive black hole, the tidal forces at the event horizon are quite gentle, and an observer could cross it without feeling anything unusual. The gravitational pull is relatively constant across the event horizon itself. The drama of the event horizon is not in the strength of the gravity at that specific location, but in its global consequence. The fact that it represents the boundary of a region from which escape is impossible. It is a causal boundary, not necessarily a physically violent one. The true violence, in the form of tidal forces, awaits much closer to the singularity for a large black hole. At the very heart of the black hole model lies the singularity, the central point where the curvature of space-time is predicted to become infinite. This is where all the mass that has ever fallen into the black hole is ultimately crushed. It is a point of zero volume, a concept that is difficult to grasp intuitively. Imagine the entire mass of a star, billions upon billions of tons, compressed into a region smaller than a single atom. In this state, our current understanding of physics completely fails. The density, temperature, and pressure would all be infinite, concepts that are likely mathematical artifacts of an incomplete theory rather than a true description of physical reality. Resolving the paradox of the singularity and describing the true nature of the matter at the center of a black hole will require a new theory of quantum gravity, one that can handle the interplay of extreme gravity and quantum mechanics in this ultimate cosmic crucible. The singularity remains one of the most profound and challenging mysteries in all of science. The task of observing the supermassive black holes at the centers of galaxies is often complicated by their surroundings. The galactic core is an incredibly dense and dusty environment. Vast clouds of interstellar gas and dust swirl around the center, acting as a thick shroud that obscures our view in visible light. This is why the center of our own Milky Way appears as a dark band in the night sky. Not because there are no stars there, but because they are hidden behind an impenetrable wall of cosmic dust. To peer through this veil, astronomers must use other wavelengths of light that can penetrate the dust, such as radio waves, infrared, and X-rays. It is only by observing in these non-visible parts of the electromagnetic spectrum that we can get a clear view of the stars orbiting the galactic center and detect the radiation from the black hole's accretion disk. This multi-wavelength approach is essential for studying these hidden monsters and unraveling the secrets of the galactic core. The process of accretion is often far messier than a simple, inexorable downward spiral. While a significant portion of the matter in an accretion disk is destined to cross the event horizon, a surprising amount can be violently ejected back into space. This expulsion is driven by a complex interplay of intense radiation pressure and powerful magnetic fields that are threaded through the disk. As matter swirls inward at incredible speeds, it is heated to millions of degrees, causing it to radiate with ferocious intensity. This outward blast of radiation can be powerful enough to counteract the inward pull of gravity for some of the gas, pushing it away. Furthermore, the rapid motion of the charged particles in the disk generates an incredibly strong and twisted magnetic field. These magnetic field lines can act like a cosmic slingshot or a particle accelerator, trapping material and then flinging it outward from the poles of the disk in the form of powerful, collimated jets. These jets can travel at speeds astonishingly close to the speed of light, carrying away a significant fraction of the mass and energy that was spiraling toward the black hole. This cosmic balancing act between inflow and outflow is a key part of the feedback mechanism that allows a black hole to regulate its own growth and the evolution of its host galaxy. The creation of the iconic image of the M87 black hole's shadow was a masterpiece of data processing and theoretical modeling. The Event Horizon Telescope did not produce a simple photograph in the traditional sense. Instead, the individual telescopes in the global array each recorded a stream of radio waves from the target. This raw data, amounting to petabytes of information, was then physically shipped on hard drives to central supercomputing facilities for processing. The challenge was to combine these disparate signals, carefully accounting for the different arrival times of the light at each telescope, to reconstruct a single, coherent image. This process, known as interferometry, is analogous to reassembling the image from a shattered mirror by analyzing the fragments of light. To validate their results, the EHT team created a detailed computer simulation of the black hole, tracing the path of millions of individual light rays, or photons, as they traveled through the warped space-time near the event horizon. They then mapped where these photons originated and where they disappeared into the black hole. The resulting simulated image, based purely on Einstein's theory of general relativity, was a near-perfect match for the image reconstructed from the observational data, providing a stunning visual confirmation of our understanding of gravity in its most extreme form. In the year 2021, the Event Horizon Telescope collaboration released a new, even more revealing image of the M87 black hole. This image was created using polarized light, which is a special property of light waves that describes their orientation. Light from the accretion disk becomes polarized when it travels through the hot, magnetized gas. By measuring this polarization, astronomers were able to map the structure of the magnetic field lines around the black hole for the first time. The image revealed a striking pattern of swirling magnetic fields, confirming a key theoretical prediction about the physics of accretion disks. It showed that the magnetic fields near the event horizon are incredibly strong enough to push back against the inflowing matter and help launch the powerful relativistic jets that extend for thousands of light years. This polarized image provided the first direct observational evidence of the crucial role that magnetic fields play in powering these colossal outflows, giving us a much more complete picture of the cosmic engine at the heart of the galaxy. It was like putting on a new pair of glasses that allowed us to see a previously invisible layer of reality. The study of black holes is a field rich with brilliant minds, and among the leading experts in the world today is the theoretical astrophysicist Priyamvada Natarajan. A professor at Yale University, she has made seminal contributions to our understanding of the formation, growth, and demographics of black holes, particularly the supermassive ones. Her work focuses on creating detailed theoretical models and cosmological simulations to explain the coevolution of black holes and galaxies. She has pioneered many of the key ideas about the origins of the first seed black holes in the early universe, and the mechanisms, such as mergers and accretion, by which they grow into the giants we see today. Her research has been instrumental in shaping our understanding of the cosmic feedback loop that regulates star formation and galaxy growth. As a prominent science communicator, she is also dedicated to making the complex and mind-bending concepts of cosmology accessible to the public, sharing the wonder and mystery of these enigmatic objects with a global audience. Her work exemplifies the crucial interplay between theoretical modeling and observational astronomy that continues to drive our exploration of the darkest corners of the universe. The question of how supermassive black holes grew so large, so quickly in the early universe remains one of the most significant unsolved problems in cosmology. One of the leading theories suggests that they may have formed from the direct collapse of a large, dense cluster of stars in the crowded centers of young galaxies, where hundreds or even thousands of massive stars were packed into a very small volume of space. A process of runaway collisions could have occurred. Stars would have repeatedly collided and merged, rapidly building up a single supermassive star. Such an object would be incredibly unstable and would quickly collapse under its own immense gravity, bypassing the normal supernova process and collapsing directly into an intermediate mass black hole. This seed black hole, already possessing a mass of thousands of suns, would then have a significant head start, allowing it to grow much more rapidly by accreting gas and merging with other black holes to become the supermassive behemoth we see at the center of the galaxy today. An alternative and more exotic theory proposes a connection between supermassive black holes and the mysterious substance known as dark matter. Dark matter is an invisible form of matter that does not interact with light, but makes up about 85% of the matter in the universe. Its gravitational influence is responsible for holding galaxies and galaxy clusters together. According to this theory, in the early universe, the immense halos of dark matter that surrounded nascent galaxies could have had incredibly dense central cores. It is possible that the dark matter particles in these cores, under the influence of their own immense gravity, could have collapsed directly to form large black hole seeds. This would provide a natural mechanism for forming massive seeds without the need for stars, potentially explaining how supermassive black holes were able to appear so early in cosmic history. This idea is still highly speculative, as it depends on the unknown properties of dark matter particles, but it represents an exciting and active area of theoretical research that connects two of the greatest mysteries in modern cosmology: the nature of dark matter and the origin of supermassive black holes. The formation of the missing link intermediate mass black holes is another area of intense study. One of the most promising theories for their creation also involves a process of runaway collisions, but in a slightly different environment. Globular clusters are ancient, incredibly dense spherical collections of hundreds of thousands of stars that orbit most large galaxies. In the ultra-dense cores of these clusters, close encounters and collisions between stars are much more common than in the sparse disk of a galaxy. A chain reaction of stellar mergers could occur, where stars repeatedly collide and coalesce, eventually forming a single, very massive star. This star would then collapse to form an intermediate mass black hole. Alternatively, an existing stellar mass black hole in the core of the cluster could grow steadily over billions of years by consuming stars that wander too close, or by merging with other stellar mass black holes. These processes provide a plausible pathway for building up black holes in the intermediate mass range, from 100 to a few thousand solar masses, within the confines of these dense stellar nurseries. The search for these elusive intermediate mass black holes has been a long and challenging one. But in the year 2014, astronomers announced a significant discovery. They found compelling evidence for an intermediate mass black hole located not in the center of a galaxy, but in the arm of a distant spiral galaxy. The object, known as M82X1, is the brightest ultraluminous X-ray source known, a class of objects that are more luminous than any known stellar process, but less luminous than the active galactic nuclei powered by supermassive black holes. By observing the periodic variations in its X-ray emission, astronomers were able to infer that it was a black hole with a mass of about 400 times that of our Sun, locked in orbit with a massive Wolf-Rayet star. This discovery provided some of the strongest evidence to date for the existence of an intermediate mass black hole, and suggested that these objects might be found not only in the centers of small galaxies or globular clusters, but also in the more dynamic environments of spiral arms. The detection of merging black holes by gravitational wave observatories has confirmed that binary black hole systems are common in the universe. But how do these systems form in the first place? There are currently two primary theories that attempt to explain their origin. The first is the isolated binary evolution model. In this scenario, two massive stars are born together as a binary pair. They live out their lives side by side, and as each star exhausts its fuel, it collapses to form a black hole. If the binary system can survive these two supernova explosions without being kicked apart, it will result in a binary black hole system. The second theory is the dynamical formation model. In this scenario, the black holes are not born together. Instead, they form from isolated stars in a dense stellar environment, like a globular cluster. Over time, through complex gravitational interactions, two black holes can encounter each other, capture each other gravitationally, and form a new binary system. Determining which of these two pathways is the dominant one for creating the merging black holes we now observe with LIGO and Virgo is a major goal of modern astrophysics. The nature of the event horizon, once thought to be a relatively benign boundary, was thrown into question by a startling theoretical proposal in 2012. A study by a group of physicists, including Joseph Polchinski, explored a seeming contradiction between Einstein's theory of general relativity and the principles of quantum mechanics, a problem known as the black hole information paradox. Their calculations suggested a radical and controversial conclusion that the event horizon might not be an empty, smooth region of spacetime, as general relativity predicts. Instead, they proposed that it could be a wall of fire, a region of incredibly high energy quanta that would instantly incinerate any object attempting to cross it. This firewall would be a direct consequence of the quantum entanglement required to preserve information. The idea remains highly contentious and is not widely accepted, as it would violate a cornerstone of general relativity known as the equivalence principle. However, the firewall paradox has sparked a decade of intense debate and research, highlighting the deep and unresolved conflicts that still exist between our two most fundamental theories of the universe, and pushing physicists to explore new and radical ideas about the true quantum nature of space-time and gravity. The mind-bending physics of black holes, particularly the extreme effects of time dilation and warped space-time, were brought to the forefront of popular culture in the 2014 science fiction film Interstellar. The filmmakers went to extraordinary lengths to ensure scientific accuracy, enlisting the renowned Caltech theoretical physicist Kip Thorne as both an executive producer and the film's science advisor. Thorne, a Nobel laureate and one of the world's foremost experts on gravitational physics, worked closely with the visual effects team to create what are still considered the most realistic depictions of a black hole and a wormhole in cinematic history. He provided the fundamental equations of general relativity, which the visual effects artists then used to write new rendering software that could accurately trace the paths of millions of light rays as they were bent by the black hole's immense gravity. The resulting images of the black hole, named Gargantua in the film, showcased bizarre visual phenomena like gravitational lensing, the photon ring, and the warped appearance of the accretion disk, providing audiences with a stunning and scientifically grounded glimpse into the strange reality near an event horizon. Thorne's involvement ensured that the film was not just a captivating story, but also a valuable and largely accurate lesson in astrophysics for millions of viewers. While black holes are defined by their ability to trap light, a profound theoretical insight from Stephen Hawking in the 1970s revealed that they are not entirely black. By applying the principles of quantum mechanics to the region just outside the event horizon, Hawking discovered that black holes should emit a faint, continuous stream of thermal radiation. This phenomenon, now known as Hawking radiation, arises from a quantum process involving virtual particles. According to quantum field theory, empty space is not truly empty, but is filled with a sea of virtual particle-antiparticle pairs that constantly pop into and out of existence. If a pair of these particles is created right at the edge of the event horizon, it is possible for one particle to fall into the black hole while the other escapes. To a distant observer, it would appear as if the black hole itself is emitting particles. This process causes the black hole to lose a tiny amount of its mass and energy over an incredibly long period. The temperature of this radiation is inversely proportional to the black hole's mass. Smaller black holes are hotter and radiate more intensely. while larger ones are colder and radiate more slowly. This discovery was revolutionary, as it was the first theory to successfully link the previously disparate fields of general relativity, quantum mechanics, and thermodynamics. The singularity at the heart of a black hole represents the ultimate frontier of our current scientific understanding. It is a point where the predictions of general relativity, our best theory of gravity, devolve into infinities, signaling a complete breakdown of the known laws of physics. Concepts like space, time, density, and temperature lose their familiar meanings. At the singularity, the gravitational field becomes infinitely strong, and space-time curvature becomes infinite. Our scientific language, built upon the physics of the observable universe, is simply inadequate to describe the conditions at this single, crushed point. To understand what truly happens at the center of a black hole, we will need a new, more comprehensive theory of quantum gravity. This future theory would unite Einstein's description of the large-scale universe with the quantum mechanics that governs the small scale, providing a self-consistent description of reality at its most extreme. Until that theoretical breakthrough is achieved, the singularity will remain an enigmatic and tantalizing symbol of the limits of human knowledge, a place where the map of physics as we know it simply ends. The astonishing feat of imaging a black hole's shadow was made possible by creating a virtual telescope the size of the Earth. The Event Horizon Telescope Array connects radio dishes across the globe, from Europe and the Americas to the South Pole. The data collected at each site is time-stamped with extreme precision using atomic clocks. When these vast data sets are later combined and correlated at a central processing facility, the signals are synchronized, effectively allowing the array to function as a single planet-sized dish. This technique of very long baseline interferometry, or VLBI, is what provides the extraordinary angular resolution needed to see the tiny shadow of a black hole in a distant galaxy. The greater the distance between the telescopes in the array, the finer the detail they can resolve. By using telescopes on different continents, separated by thousands of kilometers or thousands of miles, the EHT can achieve a resolution 1,000 times better than the Hubble Space Telescope. It is a remarkable example of how clever engineering and global collaboration can overcome physical limitations to create an instrument of unprecedented power, allowing us to probe the very edge of an event horizon millions of light years away. The first object in the sky to be widely and confidently identified as a black hole was the powerful X-ray source Cygnus X-1. Its discovery and subsequent identification in the early 1970s marked the transition of black holes from a theoretical curiosity to a legitimate and observable class of astrophysical objects. The evidence was built piece by piece. First, X-ray telescopes on rockets and satellites pinpointed the source. Then, radio telescopes identified a radio source at the same location. Finally, optical astronomers identified a massive blue supergiant star at that position and observed its telltale wobble, indicating it was orbiting an unseen companion. By measuring the star's orbit, they were able to calculate that the companion's mass was far too great for it to be a neutron star. The only remaining possibility, consistent with the laws of physics, was a black hole. The wealth of evidence for Cygnus X, 1, convinced a skeptical astronomical community and solidified the reality of these objects, paving the way for the discovery of thousands of other black hole candidates in the decades that followed. It was the first entry in a new cosmic catalog, the first confirmed sighting of a truly new and exotic kind of celestial beast. One of the most pervasive misconceptions about black holes is that they suck things in. This word implies an active process, like a vacuum cleaner drawing in dust. The reality is much more passive and is governed by the fundamental force of gravity. A black hole's gravitational pull is no different from that of any other object of the same mass, except for the fact that it is concentrated in a much smaller space. Objects do not get sucked into a black hole. They fall into it. This fall is a consequence of the object's trajectory and the curvature of space-time created by the black hole's mass. If a planet or star is on a stable orbit around a black hole at a safe distance, it will remain on that orbit indefinitely, just as the Earth orbits the Sun. It is only when an object's path brings it too close, on a decaying orbit or a direct collision course, that it will be captured by the black hole's gravity. The process is a fall, not a suction, a submission to the universal and ever-present force of gravity in its most extreme manifestation. The consequences for a star that strays too close to a supermassive black hole are catastrophic and spectacular. If a star on a wandering orbit passes within a certain distance, known as the Roche limit, the tidal forces exerted by the black hole will overwhelm the star's own gravity that holds it together. The side of the star closer to the black hole is pulled with immensely greater force than the far side. This differential pull stretches the star vertically while compressing it horizontally until it is ripped apart into a long, thin streamer of gas. This dramatic and violent process is known as a tidal disruption event. Some of the stellar debris is flung out into space at high speed, while the rest is captured by the black hole's gravity, forming a temporary, brilliant accretion disk. This disk heats up and radiates intensely across the electromagnetic spectrum, particularly in X-rays and ultraviolet light, creating a luminous flare that can be observed from millions of light years away. These events, which occur in a given galaxy roughly once every 10,000 years, provide a unique opportunity for astronomers to study the properties of otherwise dormant supermassive black holes as they are briefly illuminated by the death of a star. The evocative and now ubiquitous term black hole was not coined until relatively late in the history of the concept. It was popularized in 1967 by the American theoretical physicist John Wheeler during a conference talk. Before Wheeler's memorable coining, the scientific community used more cumbersome and less poetic phrases to describe these objects, such as gravitationally completely collapsed object, or collapser. Wheeler's simple, powerful, and descriptive term captured the public imagination and quickly became the standard nomenclature. It perfectly encapsulates the two most essential features of the object: its ability to trap light, making it black, and its nature as a deep gravitational well, a hole in the fabric of space-time from which there is no escape. The adoption of this term was a key moment in the cultural history of the object, transforming it from an obscure theoretical concept into one of the most famous and intriguing ideas in all of science. Before John Wheeler's term became standard, another name was sometimes used that reflected the strange temporal effects near the event horizon. These objects were occasionally referred to as frozen stars. This name arose from considering the perspective of a distant observer watching an object fall into a black hole. Due to the extreme gravitational time dilation near the event horizon, the object's motion would appear to slow down, its light becoming increasingly red-shifted and faint. From the outside observer's point of view, the object would seem to slow to a complete stop and freeze at the event horizon, its image remaining there for eternity, albeit becoming infinitely dim. While the falling object itself would experience no such pause and would cross the event horizon in a finite amount of time, this external perspective gave rise to the descriptive, if ultimately misleading, name of a frozen star. This older term captures a different aspect of the bizarre physics at play, focusing on the distortion of time rather than the trapping of light. The conceptual seeds of the idea of a black hole were planted long before Einstein's theory of general relativity. The first person to seriously consider the possibility of an object with gravity so strong that light could not escape was the English natural philosopher and clergyman John Michell. In a letter written in 1783 to the Royal Society, Michell, using Newton's theory of gravity and the corpuscular theory of light, reasoned that a sufficiently massive and compact star would have an escape velocity greater than the speed of light. He called these hypothetical objects dark stars. He even correctly calculated that such an object would need to have the same density as the Sun, but be 500 times larger in diameter. Although his reasoning was based on a now obsolete theory of physics, his fundamental conclusion was remarkably prescient and represents the first documented scientific speculation about the existence of what we now call black holes. It was an idea so far ahead of its time that it was largely ignored for nearly 2 centuries, a brilliant flash of insight that predated the theoretical framework needed to fully understand it. The simple, non-rotating black holes described by Carl Schwarzschild's solution to Einstein's equations are a useful theoretical starting point. But in the real universe, it is expected that all black holes should spin. This rotation is a natural consequence of their formation. The massive star or gas cloud that collapses to form the black hole would have possessed some initial angular momentum. And just as an ice skater spins faster when they pull their arms in, the conservation of angular momentum dictates that the resulting black hole must be rotating, often at incredibly high speeds. This spin adds a new layer of complexity and bizarre physics to the object. A rotating black hole, described by the Kerr solution to Einstein's equations, is not just a passive gravitational sink. Its rotation actively affects the space-time around it. The spinning mass drags the very fabric of space and time along with it, creating a swirling vortex in the geometry of the universe. This phenomenon has profound consequences for any matter or energy in the vicinity of the black hole. This twisting of space-time by a rotating mass is a remarkable effect known as frame dragging. Predicted by Einstein's theory of general relativity, it means that space itself is not a static backdrop, but a dynamic entity that can be pulled and distorted by the motion of massive objects. Near a rotating black hole, this effect is so extreme that it becomes impossible for any object to remain at rest relative to a distant observer. Space-time is being dragged around the black hole so rapidly that everything within a certain region is forced to rotate with it, no matter how powerful its rockets or engines might be. This is not a force in the conventional sense. It is a compulsory motion imposed by the geometry of space itself. Frame dragging is a subtle effect that has been measured in the weak gravitational field of Earth by satellites like Gravity Probe B. But near a rapidly spinning black hole, it becomes a dominant and inescapable feature of reality. A cosmic whirlpool that warps the fundamental structure of the universe. The region around a rotating black hole where this compulsory co-rotation occurs is known as the ergosphere. It is a squashed, oblate, spheroidal region that lies outside the event horizon. The outer boundary of the ergosphere is the static limit, the point at which it becomes impossible to stand still. The inner boundary is the event horizon itself. Unlike the event horizon, it is theoretically possible to enter the ergosphere and then escape again, provided one keeps moving and does not fall into the black hole. Within the ergosphere, space is being dragged around faster than the local speed of light relative to a distant observer, although objects within it are still moving at less than the speed of light relative to their local space-time. This bizarre region is a place of immense energy, a reservoir of the black hole's rotational kinetic energy that, in theory, could be tapped. The possibility of extracting energy from a rotating black hole's ergosphere was first proposed by the brilliant mathematical physicist Roger Penrose in 1969. The theoretical mechanism, now known as the Penrose process, is a fascinating thought experiment. It involves lowering a particle into the ergosphere and then splitting it into two pieces. If the split is timed correctly, one piece can be made to fall into the black hole on a negative energy trajectory, while the other piece is ejected from the ergosphere with more energy than the original particle had. In essence, the escaping particle has stolen some of the black hole's rotational energy. This process shows that while nothing can escape from within the event horizon, the rotational energy stored in the ergosphere, which is outside the event horizon, is not completely locked away. It is believed that a similar process involving magnetic fields rather than splitting particles may be responsible for powering the incredibly luminous jets of quasars, providing a natural mechanism for converting the rotational energy of a supermassive black hole into the colossal outflows that shape galaxies. The physical size of a black hole, as defined by the radius of its event horizon, is directly and simply related to its mass. This characteristic radius is known as the Schwarzschild radius, named after the German astronomer who found the first exact solution to Einstein's field equations. The formula is remarkably straightforward. The more massive a black hole is, the larger its event horizon. If our Sun, with a radius of about 700,000 kilometers, or 435,000 miles, were to collapse into a black hole, its Schwarzschild radius would be a mere 3 kilometers, or about 1.86 miles. A black hole with the mass of the Earth would have an event horizon the size of a small marble, just 9 millimeters, or about 0.35 inches in radius. For the supermassive black hole, Sagittarius, a star with its 4 million solar masses, the Schwarzschild radius is about 12 million kilometers, or 7.5 million miles. This direct proportionality is a fundamental feature, a simple cosmic rule that dictates the scale of these enigmatic objects. A curious and counterintuitive consequence of this relationship is that the average density of a black hole decreases as its mass increases. Density is defined as mass divided by volume. While the mass of a black hole increases, the volume enclosed by its event horizon increases even more rapidly, specifically with the cube of the radius, which is proportional to the cube of the mass. As a result, the more massive a black hole becomes, the less dense it is on average. A small stellar mass black hole has an average density far greater than that of an atomic nucleus, one of the densest forms of matter known. However, a supermassive black hole with a mass of billions of suns can have an average density that is surprisingly low, a fact that defies our intuitive understanding of these objects. This leads to the astonishing conclusion that a sufficiently large, supermassive black hole can have an average density lower than that of water, or even lower than that of air. For a black hole with a mass of about 100 million times that of the Sun, the average density within its event horizon is roughly the same as that of water. For the truly giant black holes at the centers of the largest galaxies, weighing in at tens of billions of solar masses, the average density is less than that of the air we breathe. This does not mean the black hole is a fluffy cloud. All its mass is still concentrated at the central singularity. It simply means that the volume defined by its vast event horizon is so enormous that the mass to volume ratio is very low. This also explains why the tidal forces at the event horizon of a supermassive black hole are so gentle. One could, in principle, drift across the event horizon of such a giant without noticing, entering a region with the average density of a light fog, only to be inevitably drawn toward the incomprehensible reality of the singularity within. The defining characteristic of the event horizon is its absolute finality. It is the ultimate one-way street. Anything that crosses this boundary, whether it is a particle of matter, a beam of light, or a piece of information, can never escape. This is not a limitation of technology. It is a fundamental feature of the structure of space-time. Once inside the event horizon, all possible future paths, all world lines, lead inevitably to the central singularity. The flow of space-time itself is directed inward, like a river plunging over a waterfall. To escape would require traveling faster than the speed of light, which is a physical impossibility. This absolute nature of the event horizon is what makes black holes such perfect prisons, causally disconnecting their interiors from the rest of the universe. The information, matter, and energy that fall in are, from the perspective of an outside observer, lost from the cosmos forever. The concept of the black hole, with its profound and unsettling implications, has resonated far beyond the world of science, becoming a powerful and enduring motif in popular culture. For decades, it has been a staple of science fiction, serving as a versatile plot device for everything from a cosmic hazard and a source of immense power to a gateway for interstellar travel or a portal to other dimensions. In films, books, and television shows, black holes have represented the ultimate unknown, a symbol of the universe's most extreme and mysterious frontiers. This cultural fascination reflects a deep human curiosity about the fundamental nature of reality, the limits of knowledge, and our place in a cosmos that is far stranger and more wonderful than we can possibly imagine. The black hole is more than just an astrophysical object. It is a modern myth, a scientific concept that has taken on a life of its own in the collective imagination. Despite a century of progress since their prediction by Einstein, the study of black holes continues to be a vibrant and active area of research at the forefront of physics and astronomy. Many profound mysteries remain to be solved. What is the true nature of the singularity? How can the conflict between general relativity and quantum mechanics, embodied in the information paradox, be resolved? What role did primordial black holes play in the early universe? And could they be the elusive dark matter? How exactly do supermassive black holes form and grow? And what is the full extent of their influence on the evolution of galaxies? These are some of the grand challenges that will occupy scientists for generations to come. Each new observation, from the detection of gravitational waves to the imaging of an event horizon provides a new piece of the puzzle, but also raises new and deeper questions. The black hole, once a mere theoretical curiosity, has become a central player in our quest to understand the ultimate laws of the universe, a dark and silent guide leading us toward a new and more complete understanding of the cosmos. And so, our journey through the warped and silent landscapes of space-time draws to a close. We have traveled from a flicker of an idea in the mind of a prescient 18th century clergyman through the revolutionary equations of a 20th century genius to the very edge of an event horizon, captured by a telescope the size of a world. We have seen how these silent behemoths are born in the cataclysmic death of stars, and how they grow to become the gravitational anchors of entire galaxies. We have witnessed their power to bend light, to stretch time, and to tear apart entire suns, all while remaining utterly, perfectly invisible. Yet, for all that we have learned, the black hole remains the ultimate frontier, a place where our most fundamental descriptions of reality cease to make sense. It is the cosmic crucible where the immense gravity of the universe, as described by general relativity, collides with the strange and subtle rules of the quantum world. The singularity at its heart is not just a point in space, but a profound question mark hanging over the future of physics, beckoning us toward a new and more complete understanding of creation. The story of the black hole is, in the end, a story about the relentless power of human curiosity. It is a testament to our ability to probe the universe's deepest secrets, to see the unseeable, and to comprehend the incomprehensible. The next time you find yourself under a clear, dark sky, take a moment to look up at the familiar constellations and the faint, shimmering river of the Milky Way, and remember what lies unseen within that celestial tapestry: the silent gravitational wells, the ripples in space-time from ancient collisions, and the deep, dark sources of unending creation, where the story of our universe is still being written. Remember that the greatest mysteries are often found not in the light, but in the profound and illuminating darkness that surrounds it. Thank you for listening.